Alright, so here we are to talk about weak acids and bases, section 16.5 and 6, section 16.6 of your textbook. So far we've learned about strong acids and strong bases, and for example, HCl is a strong acid which completely dissociates to become H plus and Cl minus. And weak acids, an example of that would be like hydrofluoric acid, which would partially dissociate to become H plus and F minus. Now if we wrote ICE tables for each of these, ICE, initial change equilibrium tables, and let's say that we had 10 moles of this one and 10 moles of this one to start with, none, 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 and none. For a strong acid, we would lose all of this. We would lose all of the strong acid, and we would gain the same amount on the right-hand side. And you would, in effect, end up with none of this molecular substance at the end, and you'd end up with 10 and 10, or lots of this stuff over here on the right-hand side. And you can see that, you know, H plus is the thing we're really interested in, because that gets me into the pH square over here, and now I can calculate the pH, and log of 10 is, you know, negative log of 10. I'd end up with like a -1 pH, so it would be like super, super acidic, and there'd be lots and lots of this H plus. Weaks, on the other hand, would only lose a small, small amount. Small, small amount. And so when I lost this, or there'd be a change, I would lose like maybe 0.1 amounts of this. And I would only gain like 0.1 and 0.1 of each of these. So I'd end up with like 9.9, almost as much as I started with. In this one, I'd end up with 0.1 here and 0.1 here. And now, if I were to find the pH of this one, pH would be equal to the negative log of 1 times 10 to the negative first. I'd end up with a pH of 1. So you can see that even though I started with the same amount, because it's a weak, it only partially dissociates. As a matter of fact, you only dissociate a tiny bit. Turns out that tiny bit makes a difference because, I mean, a pH of 1 is still quite acidic. And so even though I only lost a little bit, I still changed the pH significantly. So weak acids and bases all do this, where they only partially dissociate, and ICE tables become super important in determining what the pH of that solution is. Let's work a sample problem now. In the sample problem, we're going to work a sample exercise 16.10 from your textbook. And it's on page 688 if you're in the 13th edition. If you're in a different edition or a different textbook, you could still work this same problem. I'm going to zoom in just a little bit. We'll take a look at the question. And it says, a student prepares a 0.1 molar solution of formic acid, HCOOH, and found its pH to be 2.38. Calculate the K for the formic acid at this temperature. So step number one, whenever you're working these types of problems, is to always write the weak acid or the weak base forming into a solution of water. So our weak acid in this case is HCOOH, and when in doubt, react it with water. Always write it that it's going to become a solution, or it's going to become aqueous. And since this is a carboxylic acid, C double bond OOH, this H would then be donated to the water, and we'd end up with H3O plus over here on the right-hand side, and some HCOO minus on the right-hand side. Writing that equilibrium equation is always the first step in solving these types of problems. Next, make an ICE table and put in the information that you know. So we reread the question, and we find out that it's a 0.1 molar solution, so it's 0.1 right here. Water, of course, is a pure liquid, and pure liquids and pure solids never go into the equilibrium constant expression. And so you can just put dashes for those, because they never involve any of the calculations that we're going to do for water as a pure liquid. Since they don't tell you anything about the products over here in the question, we have to assume that there are none of them. So I can put 0 and 0 there to start with. That's a handy assumption that you have to become kind of taught to make, that since they don't say anything about them, there's 0 and 0. Now they give us some other data in the question. They tell us the pH is 2.38. I'm going to write that down here at the bottom. And I have to be really familiar with my pH square, because if I know the pH, what could I find from the pH square that would be in this balanced equation? Notice I could go from pH to this thing called H+, which is also known as H3O+, also known as a proton, also known as the hydronium ion. Has like 4 or 5 different names and they all mean the same thing. And moving from one to the other would then allow me to find the equilibrium amount right here of H3O+. And to find the K, I need products divided by reactant to the power of the coefficients at equilibrium, because it's the equilibrium constant, so I need the values at equilibrium. So, undoing this pH, I would do 10 to the negative 2.38 to find the H+ ion concentration. And if I do that on my calculator, I end up with H+ equaling 0.00417. I can now take this number and put it into my ICE table for H+. So this is 0.00417. And since this is a 1:1 ratio, however much I have here, I also have right here. So I also have 0.00417. And working backwards just to complete the entire ICE table, since I started with 0, I had to gain 0.00417 here, and I had to gain 0.00417 here. Which leads me to the other side, because whatever I gained on this side, I had to lose from this side. And since it's a 1:1 ratio here, I must have lost 0.00417 right here. 0.1 minus this number ends up being 0.0958. And now I have enough information between those 3 values to calculate the equilibrium constant, because the equilibrium constant is going to be equal to products, H3O+, times HCOO minus, divided by reactants. My reactants is HCOOH. And I have to make sure to put the equilibrium values in there. H3O+ is this number. And as a savvy math student, I recognize that both those numbers are the same, so I could write this as this number squared, those 2 multiplied together, and then I would put in 0.0958 here on the bottom, square that, divide it by that, I end up with approximately 1.8 times 10 to the negative 4th. Now this K is given a special name since it's the equilibrium constant for an acid. I now call it K with a little a down below it. A stands for acid. It's the equilibrium constant for the weak acid called formic acid. So notice how I was given some data, pH, and I was given an initial concentration, and from that I could find the equilibrium constant for that substance. Now a second calculation that arises from this is the calculation of what's called percentage ionization. Percentage ionization is an indication of how much does this acid break apart into ions. And this is equal to the concentration of the H+ at equilibrium divided by the concentration of the acid initially times 100%. And for this acid that I just did, my H+ ion concentration is 0.00417. The concentration of my acid originally was 0.1, and then I'd multiply that by 100, and if I do that math, I end up with approximately 4.17% ionized. Now, You can also find the percent ionization for a weak base. But acids are known for their H+, and since it's a base, I would need to know the OH- at equilibrium. So this equation changes to become OH- at equilibrium divided by the concentration of the base initially times 100%. So it's the same kind of equation. It's just a matter of now I'm looking at the ion that is more prominent in basic solutions versus the ion that's prominent in acidic solutions. So one of the trick questions on one of your homework pieces is they give you a different value to solve for. They don't ask you to find the percent ionization. They tell you the percent ionization of a weak base is, for example, 10%. And they tell you the initial concentration of that weak base is, let's say 0.05 molar. If they told you these two items, which thing could I find from this equation? The 10% would go right here. The 0.05 molar would be initial. Which value do I not know? The OH- at equilibrium, right? They might not ask for the OH- at equilibrium. They might ask, what's the pH at equilibrium? Oh, okay. So you could find the OH- from this, then you'd have to go into the pH square and go one of the other ways to find the pH. Watch for that on a homework problem. Let's do one more example problem, but this time for a weak base. We're going to be on page 697 of your textbook, and we're going to do sample exercise 16.15. I'm going to change the question just slightly to add another piece in so you can see another example. It's interesting to look at these weak bases that they give in a table. You can see for the weak bases, they also give an equilibrium constant value, but notice it's called K with a little b down below it. It's not Ka anymore. Now it's called Kb, and of course the b stands for base, right? So it's the equilibrium constant for a weak base. Notice how here is one that has an NH2 with an unshared pair of electrons. Here's another one, NH2 with an unshared pair of electrons. You can see here's another N with unshared pair of, notice how nitrogen is very prominent in those weak bases. You can also see some of these that have ion charges to them. Ion charge, ion charge. So there are ones with lots of unshared pairs of electrons that would be good acceptors of protons. All right, let's work this sample exercise 16.15. It says, calculate the concentration of OH- in a 0.15 molar solution of NH3. I'm going to change the question to calculate the pH, because that involves one more step. We're still going to have to find the OH-, but once we find that, how would you find the pH? We'll have to do that in the problem since I'm asking that. All right, zooming out, the same steps as we did with the other weak substance, except this is a weak base. And so take the formula of your weak base, and when in doubt, react it with water. When in doubt, react it with water. Since it's a base, it's going to be a proton acceptor or a hydrogen acceptor, so the water donates the proton, and we end up with NH4 with a plus sign. And what's left over after the acid has released its proton is the OH-, and this would be our conjugate base on the right-hand side. Now, identifying what species is interesting in these types of equations is critical. And if you ultimately want to find the pH, which thing in this equation would be helpful for me finding the pH? Would NH4 be on this chart and help me find pH? Would OH- be on this chart and help me find pH? Oh yeah. So that's the thing ultimately that I want to find. Then I can get into the chart and I can move to pH. Let's make an ICE table. Reread the question. They tell me that it has a 0.15 molar solution. So over here, 0.15 molar. Water, of course, is a pure liquid, and pure liquids are never in an equilibrium constant expression, so you can just put dashes for that. And they don't tell me anything about either of these being present at the beginning, so I can put 0 and 0. Ultimately, I want to find this down here, but they don't give me any other data. And so now I have to use my favorite letter from math class, and I will lose that amount here. I will gain that amount here, and I will gain that amount here because it's a 1 to 1 to 1 ratio. At equilibrium, I will have 0.15 minus x, x amount, and x amount. And from that, I can write the K expression. And the K expression would be products, NH4 plus times OH minus divided by NH3. Don't put water in there, remember, because it's a pure liquid. And one thing they don't tell you in the question, but they expect you to look up, is to look on a table like this and find the K value. So on here, the K value is given on this chart. There's also an appendix in the back of the book to find what K sub B would be. And for us, it's for ammonia, it's 1.8 times 10 to the negative fifth. Now I could take the values that I wrote in terms of x and plug those in. And this value goes down here. And sliding this up, I would have x times x on the top divided by 0.15 minus x on the bottom, and that equals 1.8 times 10 to the negative fifth. X times x is x squared. And now I'm recognizing that I'm going to have a zoo of an equation to solve because I have an x squared, a regular x, and some number, and I would have to do the quadratic equation to solve this. So we look for easy ways to solve this rather than having to do a quadratic equation. And if you remember way back to the very beginning of this lecture, when we first talked about weak acids and bases, we said that they don't dissociate very much. As a matter of fact, looking back at your notes, we said that only a tiny bit of this would be dissociated. Only a tiny bit of the 10 would become this over here. Well, this x right here represents that tiny bit. This is small compared to this 0.15. And so to make the math easier to solve, we're going to assume that this x right here is small. And if we assume that it's small, we can ignore it, and we can write the equation as x squared divided by 0.15 right now, and we'll get pretty close to what the actual answer actually is. So solving this equation right now for x, I end up with x equaling 0.001643. And what does this actually tell us? Well, look back at the question, look back at your table. X is this. That's super helpful because if I know the OH minus ion concentration, I can now get into the pH square. And I could go from OH minus to POH to pH. And you learned how to do this without a calculator. So POH would be equal to the negative logarithm of 1.643 times 10 to the negative third. You could expand this logarithm to be negative log of 1.6 approximately plus the negative log of 10 to the negative third. This would be 3. Making a guess here, this is log of 1 is 0, of course, so pick something a little bit more than that, maybe like 0.1, and remember that's got a negative sign in front of it. This is a negative times a negative, so it's positive. So negative 0.1 plus 3, I end up with a pOH of approximately 2.9. And if I want the pH, of course I do 14 minus that 2.9, and I end up with a pH of about 11.1. Good luck with your weak acid and base problems.